let's take a look at two similar molecules. We have pyridine and pyrrole. We've seen pyridine before as a base. We've used it in our reactions, right? It's excellent at capturing chloride, once it's protonated. Although we don't usually use pyrrole as a base. And we're going to see why. These are very similar molecules, right? They're heterocycles, meaning we have a heteroatom as part of a ring. We're going to see that both of these molecules are aromatic. The pyridine may be easy to see. It looks like benzene. We've just thrown a nitrogen in there. No problem. Aromatic still. However, pyrrole is aromatic. But why? Why would pyrrole be aromatic? The reason being, this pyrrole has kind of two options of what to do with the lone pair on the nitrogen. Notice that both of these nitrogens have lone pairs. And we're going to see that the lone pair on a heteroatom is able to contribute to aromaticity. So if a heteroatom, usually oxygen, nitrogen, or sulfur, those are probably the most common ones you see in cyclic compounds, can contribute its lone pair to the aromaticity of a compound it will. And I'm going to put a little asterisk on that. So we know that pyrrole can resonate, right? We can resonate this molecule such that we'll end up with having we're going to have this negative charge here, right? We see here that now we have very clearly shown that this is very much the same as the cyclobentadiene anion. We have a negative charge on a lone pair that can rehybridize to make a p orbital. That lone pair on the nitrogen can also rehybridize. Even though that nitrogen should be sp3, it can rehybridize itself to sp2 to put its lone pair in a p orbital to allow it to resonate and overlap with the rest of the molecule. And as a result, we're going to see that it's going to be aromatic, even so. In the case of pyridine, we have to understand that it's already aromatic as it is. So it doesn't make sense for the lone pair to contribute, because at that point it would become anti-aromatic if it tried to do that. But it also can't, because if we take a closer look at pyridine, we see that this is already an sp2 orbital. It can't rehybridize itself. Because it's already got that double bond to it, holding it in place, it's already got p orbitals that are overlapping with other carbons. So this lone pair is stuck in an sp2 hybridized center. So it can't rehybridize. Or rather, that lone pair is stuck in sp2 because the p orbitals of the nitrogen are already bonding with the other carbon on its left there. Remember that to form a double bond, we have to have p orbitals overlapping. So that lone pair is stuck in an sp2 orbital. It can't hybridize. It's pointing away from the molecule also. So remember, a p orbital is straight up and down, so it's able to overlap with things. If you have one that's completely stuck out here, how are you going to overlap these two? Sorry, my hands are... How are you going to overlap these two? These you can overlap. These you cannot. No matter how much you try and wiggle them, there's no overlapping happening. So that lone pair can't contribute anyway. Even if it wanted to, it cannot. Although, it's a bad decision for it to do so anyway, it's already aromatic as it is. Let's look at some of the effects that this has on these two compounds' abilities to act as bases. We see that if pyridine grabs a proton, versus if pyrrole grabs a proton, let's see what happens. Are these two ions aromatic or not? Well, if you look at the case of pyridinium, the positive pyridine, on the left, we see that it's still got 6 pi electrons in a continuous overlapping series of p orbitals in a ring that's planar. And there's still 6 pi electrons. So, still aromatic. So, check. No problem. However, with pyrrole, we saw that that lone pair was what allowed the molecule to become aromatic. And so if we use that lone pair to abstract a base or abstract a proton from an acid, we see that this is now non-aromatic, right? It no longer has, or rather it's going to be, it's non-aromatic because we have an sp3 nitrogen here. So it's not anti-aromatic because it's not an empty p orbital. That's only for carbocations. This is a nitrogen cation that's still sp3. So we're going to have a non-aromatic species. So we went from aromatic to non-aromatic by grabbing that proton. So not a good thing. As a result, we don't really see pyrrole acting as a base. We're going to see the pKa of this thing is like that of a strong acid. It's very happy to get rid of that proton because that proton caused it to lose its aromaticity. And so as a result, pyrrole is a terrible base. The pyridinium has a pKa of about 5 or so. So we see, again, this difference in very similar molecules that we have about a 100,000 preference of 1 to 100,000 for keeping your aromaticity here. So we're going to investigate this further when we look at bases, it's specifically when we talk about amines in the amines chapter. But it's important to note that we also have to consider aromaticity now when we're looking at acid-base behavior. So we saw that the cyclopentadiene has a very acidic proton, an exceptionally acidic proton, because removing that proton leads to aromaticity. And now with pyrrole, the nitrogen analog, we see that we want it to not function as a base. It's a very poor base, an unexpectedly bad base, because acting as a base causes it to lose aromaticity. So there's a lot of ramifications for aromaticity because molecules will always try and get it if they can. And so kind of in summary of this section, molecules will do what they can to be aromatic. They will try to prevent becoming either non-aromatic or anti-aromatic. Anti-aromatic is the worst situation that a molecule can be in. So they will either avoid it in the first place by not reacting, or they will do something with their configuration, as in that cyclooctatetraene bending itself up, distorting its bond angles to avoid anti-aromaticity. So really the only way we can get truly anti-aromatic compounds is by forcing them to react, or having fixed planar molecules that are not able to bend. And so as a result, It's not very common that we see anti-aromatics. They'll try and be non-aromatic instead. But we will see that molecules will have ramifications in their reactivity based on their aromaticity or lack thereof. And so next week, we're going to go ahead and take a look at reactions of aromatic compounds. We'll start with a few basic ones, and then we'll start talking about substitution on aromatic positions.